Hello, everyone. I was asked last week to do a lesson on trigonometric identities. And so I've put together this GeoGebra applet, and what we're going to try and do is establish some of the basic GeoGebra, some of the basic trigonometric identities, and work towards the so-called double angle formulae. Okay. So let's get started. What we have here is our old friend, the unit circle. Unit because all of the points around the circle are distance 1 from the origin. And here I have my point C, which is on the circle, and moving it around. And you might ask why I've got the arrow on the theta angle here. That's because I'm measuring the angle in an anti-clockwise fashion. If the angle is measured anti-clockwise, it's positive, and that'll come up a little bit later. If it's measured the other way, it's negative. So as I move the point around, one of the things we discussed when we were doing our trigonometric review earlier in this series was that the cosine function tells you the horizontal distance from the origin for the given value of theta. So as theta goes from small to large, the distance from the origin goes down, it becomes negative, and then it goes to positive, and then back to negative. Sine theta is the y coordinate, the height of this right-angled triangle. Okay, so what do we mean when we say trigonometric identities? What we're going to use is the ideas behind symmetry and use that symmetry to find out properties of these functions in an algebra context, but always remembering the picture where it comes from. Whenever we're studying trigonometric identities, it's tempting to just memorize them. But the easiest way to memorize them, ironically enough, is to think about this picture. And by thinking about the picture, you'll be able to understand not only what the identities are, but where they come from. Okay, that's one of the cool things about trig identities. It's this fusion of geometry and algebra together. Okay, so let's get started. The first thing I'm going to do is I'm going to draw this rectangle. What is this rectangle? Where does it come about? Well, think about, as I move the point around the circle, think about how each of the other points are found. So let's start by thinking about this point. Well, this line is always horizontal. So I'm just connecting it to the other side of the circle, a reflection across the y-axis. Whereas this point down here is a reflection across the x-axis. And then if I do that again, if I reflect across the x and across the y, or across the y and then across the x, I get this point down here. So we're now going to think about these points one at a time and think about what we know about them given what we know about this point. We know this angle theta, and if we plug in theta into here, we're going to get theta into cosine, we'll get its x value, theta into sine, we'll get its y value, and that will help us derive the point. So what about this point? Let's load this one up. Now, thinking about it in terms of reflection, this angle theta here is the same as this angle theta down here. And in this context, a half circle rotation is pi radians. I'm going to be giving this lesson in radians because we're grown-up mathematicians now. This all the way around is pi, so this angle here is pi minus theta. Okay. So if this is pi minus theta, this is the angle, and that's going to work in the same way that theta works over here. So if I want to know the x value of this coordinate, instead of putting theta into cosine to find this segment, I put this angle into cosine, and that will find this distance. It'll be negative, but in the same way that theta goes into cosine to find the x, well then pi minus theta is going to find this x. Similarly, if I put pi minus theta into sine, I'll find the y value. But that's not what I've written up here. What I've written up here is the value of the point when I reflect it. When you reflect something across the y-axis, the y value stays the same. So that's the sine theta, you see, that's the same in both points. But the x values become negative. So this was cos theta, and now it's minus cos theta. Okay, so what does that mean for us? It means we have our first two trig identities, and I'm going to turn them on here. This one and this one. Sine of pi minus theta, the height of the point when you go pi minus theta radians around the circle, is the same as the height of just going theta. This distance is the same as this distance, and it's in the same direction. On the other hand, cos of pi minus theta is the opposite. Cos theta is this way. Cos of pi minus theta is the same value, but negative. So this minus cos theta gets identified with the x value of cos of pi minus theta. So cos pi minus theta, that's this distance, is the same as, and direction is the same as this one, only negative. So that's our first trigonometric identity. It means that if you know sine of one of these sides, you can find sine of the other, because they're equal up to sine. SIGN, that is. These ones are the same, these ones are opposite sign. Okay, so that was this point. What about this point down here? Now remember what I said in terms of finding the cos and the sine value. If I reflect it in the x-axis and then the y-axis, or y and then x, I end up taking the negative of both the x and the y coordinates, which is why this point down here is minus cos theta minus sine theta. Both of them become the negative of the original point up here. But by the exact same token as we were thinking about before, if this is theta, this is theta as well. You can think of them being vertically opposite angles. And this orange angle that goes all the way around here is pi radians plus an extra theta. It doesn't matter where we are. It will always be the case that this point is both minus cos theta and minus sine theta. But at the same time, the x value is cos of this angle, and the y value is sine of this angle. That allows us to establish our next two trigonometric identities, and I'll turn them on now, this one and this one. Sine of pi plus theta, what is the vertical height when I am pi plus theta radians around the unit circle? And the answer is, it's the negative of the height that I am when I only go theta radians around the circle. What's my horizontal distance when I go pi plus theta radians around the unit circle, all the way around to here? The answer, it's the negative of the amount of the horizontal distance when I only go theta radians around the unit circle. Okay, and you guessed what's coming next. I'm going to turn this one off and turn this one on. This one is cool because it gives us two identities. The first one is going to be the same as we did before, but there's going to be another one as well. So let's think about it the same way that we thought about the previous 2 points. First of all, think about it in terms of a reflection. If I reflect this point across the x-axis, the x value stays the same, but the y value becomes negative. I haven't moved across the x-axis, but however high I am now negative that high and that low down the y-axis. But I can still think about it in terms of functions. This time, though, notice that I've got minus theta because I'm going backwards. Instead of measuring the angle anti-clockwise like we always do, I'm measuring this angle clockwise, so it's the negative. So this is minus theta, and I can also think of this big angle here as being a full revolution, 2 pi, minus theta. So I get this sort of Pac-Man shape. Okay. So once again, we think about it in terms of what horizontal distance am I when I go 2 pi minus theta, so 2 pi all the way around, and then minus theta radians around the unit circle. So I go from here all the way around, and then I come back to here by going minus theta, and I say, how far across am I in terms of horizontal distance? And the answer is, I am the same as if I just went theta radians around. Starting here, going all the way around and coming back lands me the same horizontal distance away from the origin as if I'd just gone theta degrees to begin with. Now, what about vertical height? What vertical height am I when I go all the way around the unit circle by 2 pi minus 2 pi radians and then minus theta? Well, I am the opposite in terms of height. As high as I am up here, I am that low down here. And that's our final trig identity for this section when I'm thinking about it this way. But as I said, there's a cool bonus identity when we're taking a look at this, and it comes about because of this minus theta. We're going to use this in a little bit. So this time, instead of thinking about it as 2 pi minus theta radians, we're just going to think about it as minus theta. So if I start here on the unit circle and go minus theta radians, or what is my horizontal distance compared to going positive theta radians? What about my vertical height? It ends up being the same layout as these two identities, except instead of writing 2 pi minus theta, we're just going to write minus theta. So that's where I get these two identities from. Sine of minus theta, the height that I am when I go minus theta radians around the unit circle, is the negative of the height of going positive theta radians around the unit circle. What about my horizontal distance? Well, going minus theta or going plus theta doesn't make a difference. I'm the same horizontal distance from the origin, whether I go plus theta or minus theta. Okay. So these identities here are called periodicity identities, if you want to know the technical term. And you can see that there's a pattern to them. Sine, minus sine, minus sine, sine. Minus cos, cos, cos. And it sort of repeats in that fashion. And that mirrors what we get when we go like this. So here we've got cos is positive and sine is positive. And then when we go around to here, we have sine being positive and cos being negative. And then in this quadrant down here, they're both negative. Sorry, my construction's breaking at this point. And then over around to here, the sine is negative and the cos is positive. And there we go, back to normality. So each of these identities are really important, and they'll allow us to play with and manipulate trig equations and trigonometric expressions in interesting ways. Should you memorize this list of 8 equations? Absolutely not. No way. Instead, take a picture of this setup in your mind. I'll see what it looks like when I turn them all on. There we go. Yeah. So in our mind, we can see that we have our thetas here, 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 and this is our minus theta. We've got the, let me just move some of these labels around so we can see a bit better. This one here, this one here. So this is theta. So that means that this point is pi minus theta, or the sine and the cos of that angle. What about this point? That's the one that I get when I go pi plus theta, and then that lands us over here. When I go 2 pi minus theta, that's the same as going minus theta, and that lands me over here. And I can just tell, compared to this point has the same height, and these 2 points have the negative of that height. These 2 points have the same horizontal distance, and these 2 points have the negative of that horizontal distance. And by thinking about this picture, you'll be able to pull out whatever identity you need when you need it. And pictures are a lot easier to memorize than a list of equations. Okay, so what's the next step? Ah, yes, that's the next step. Okay, so this time we're not going to be talking about the rectangle. We're going to think about a different kind of symmetry to get the next identity along. This time, I'm going to take this point here and I'm going to reflect it in the line y equals x. That's this dashed line that's got a gradient of 1 passing through the origin. So as I move this point around, you can see how the triangle is moving over on the other side. Okay, I've labeled this point C prime. It's the point that I get when I reflect it. And this point here, this point should really be labeled B prime. So I'm just going to fix that up quickly. So when I reflect it across this line, before I was reflecting across the axes, but this time I'm reflecting it across this line. So you can see how the we don't have a rectangle this time. Instead, we have 2 mirror images of the same triangle. But one thing you'll notice is that here it says cos theta sine theta, and over here it says sine theta cos theta. Why is that? Whenever we reflect in the line y equals x, all we have to do is swap the x and y values. So what's the point 1, 0 when we reflect it in the line y equals x? Well, 1, 0 becomes 0, 1, and that matches with our intuition. What about this point here? This point here is about 0.6, 0.3, I suppose. 0.6 in horizontal distance and 0.3 in height. And if I were to reflect it across that line, I land myself there. There we go. That you can just imagine a line connecting those. And that is the opposite. I've swapped it around. So 0.3, 0.6 rather than 0.6, 0.3. It's just a general principle. If you reflect in the line y equals x, all you do is you swap the x and y value. So it doesn't really matter what the value of theta is. I've just swapped them. Okay. Now you'll notice though, that this time I've labeled the angle as minus theta. And that's because in the mirror universe, I'm now measuring my angle backwards. Instead of measuring it anti-clockwise, the positive direction, that angle's now measured in the negative direction. Okay. What this means for us is that I can take this point C and drop it down. Dropping this perpendicular down gives me a new right-angled triangle. And let's turn this on. This point Q isn't the reflection of anything from the original universe, but you can see as I move this point around that we still have this original reflected triangle, but now I've made a new triangle, a new right-angled triangle. So a rectangle's come back this time. This rectangle's a bit different. It's not centered on the origin, but this rectangle here is the way that we can calculate our horizontal distance and our vertical height using sine and cosine in the same way that we do height and horizontal distance using sine and cosine for this original triangle. So let's think about using this new triangle to calculate the sine and cosine value of this point a different way. Well, since this is minus theta, and I know that a right angle is pi over 2 radians, then the angle that I've got marked here is pi over 2 minus theta. So I go 90 degrees or pi on 2 radians, and then I go minus theta, and that gives me this segment here. So if I want this horizontal distance and I want this vertical height, then I can use sine and cosine as always. I'll have to excuse my cat. Come on, there we go. It's very cold. She likes to sit on my lap while I give math lectures. Living the dream. So pi over 2 minus theta, I put that into cosine and it will tell me this horizontal distance from the origin to point Q. If I put pi over 2 minus theta into sine, it will tell me the vertical height. And that is how we get our next two trig identities, this one and this one. It's a little bit in the way here, so I'm just going to move it so the line doesn't get in the way for now. If I want to know the height of my point that's traveling around the unit circle, if I go pi over 2 minus theta degrees, well, the height is the same as cos theta. This cos theta came about because I swapped the x and y values when I did my symmetry. So the height, and we can think about it as the height of the point when you go pi over 2 minus theta is equal to the original distance. And you can think about the fact that this distance here from A to B is the same as the distance from A to B prime. But that's why this, we change from sine to cos. All of these previous identities that we found was just sines turning into other sines and cosines turning into other cosines. But this time, because we have a horizontal distance turning into a vertical height, well, now if I want the vertical height of this reflected point, that's the same as the horizontal distance of the original point. Similarly here, this says that the horizontal distance of the new point is the vertical height of the old point, that this length from B to C is the same as the length from A to Q. And that's going to be true no matter where we move this point around. We are always going to be able to find what is sine of pi on 2 minus theta. Well, we just need to swap the sine for a cosine and get rid of the pi over 2 minus, and we'll get the same value. Okay, so I'm going to move these back into position because I've got some things coming up soon, and I've got one more to go. So I will get rid of this and this and this. And the next one is, so before we talked about reflecting in the x-axis, reflecting in the y-axis, doing both and landing down here. Now we've done reflecting in the line y equals x. How about now we do rotating this point by pi over 2 radians, by a right angle. So let's do this final step. I'm going to take this point. I start off by going theta radians, sorry. And then I go another right angle around. So this is my theta, and then another pi over 2 radians. And just like before, when I get to that new point, wherever it happens to be, I can make a new triangle that's going to work just like this triangle here. If I know what this angle is, I put this angle into sine and cosine, and it's going to tell me the vertical height and the horizontal distance. But you'll notice I've already put this up. How do I know that this is true? Well, all I've done is I've rotated this triangle, but this distance here, this vertical height, the sine theta, is equal to this distance here. So what is the horizontal distance of this new point? Well, it's going backwards, so it's minus the height of the original point, minus sine theta. What's the height of this new point? The height of the new point is the same as the horizontal distance of the old point. So I just need to remember which one I need to turn on here. Is it this one? Yes. So I know that that angle is theta, and that means that this angle is pi over 2 plus theta. I can think about it in two different ways. Well, let me just move that theta label. Either I have this little green theta here plus the right angle, or I think about going the right angle to get from this point to from the x-axis to the y-axis, and then going an additional theta degrees. Once I've done that, is this the point that I'm looking for? Yeah, sorry, I should have had that point beforehand. So the distance, if I throw pi over 2 plus theta, so I start by going theta and then I go pi over 2 radians more, if I put that into the cosine function, I will get this value here, because cosine always tells us the horizontal distance. And so that's this trig identity here. Similarly, if I want to know the height of my new point, I just put pi over 2 plus theta into sine. But that gives me the same value as the original horizontal distance of the original point. Okay, so now we have gathered together the first steps in our trig identities. And once again, each time, the best thing to do is to memorize the picture. Trying to memorize these two equations, you're begging for trouble. Oh, this one has sine, and this one has a cos, and this one's got a plus, and then, oh, but if it's cos and it's plus, then it's minus, like without any context, without any picture in your head. It's going to be difficult to memorize this. I mean, maybe you can. And if you can, awesome. There are some people who can do all of this stuff, but you're probably not watching videos like this. I think that, but even for those people, let's say you can sit there and memorize things. People memorize the craziest stuff, memorizing thousands of digits of pi or whatever. The important thing is that if we can think about it in terms of geometry and think about it in terms of pictures, it helps develop our intuition, helps us be better mathematicians, and helps us always make sure that we can see the connections as they're coming up. Okay, so now I have sine of pi over 2 plus theta is equal to cos theta, and cos of pi over 2 plus theta is minus sine theta. So in the future you go, oh, what's this thing? I don't remember. You can just quickly draw yourself a diagram. You can say, okay, well, imagine this is theta here, and then I'm going to go an extra 90 degrees or an extra pi over 2 radians around the unit circle. And what can I say about the point now? Well, its height is going to be equal to the original horizontal distance, and its horizontal distance is going to be the negative of the original's height. And this is going to be true no matter where we move this point around the circle. If you think about it in terms of a picture and you understand all of the parts of the equation and how they work together, you won't get confused and make a sign error or just completely go blank and not understand how to approach these things. So there are two ways to think about trig identities. The first one is to think about it being a statement in terms of a concise number of symbols about some geometrical fact. But we can also think about them as useful tools which we build upon and think about to unlock even more understanding and even more knowledge. And we're going to take a look at how the double angle formulae come about. And because we've done the groundwork and laid out these trigonometric identities, we're going to see each of these, we're going to see a couple of these come up again, but we can be on the lookout and think to ourselves, ah, that's one of those useful situations. So before I go any further, I just want to highlight one thing that I mentioned before. All of the first 8 identities that we found allow us to manipulate the arguments of sine. So if I have theta and instead I want something that looks like this or the other way around, these are sort of the rules that I'm allowed to sort of play with them. But none of these original 8 identities change the sine or the cos. So thinking about it from an analytical or an algebraic frame of mind, these can help us turn sines into causes and turn causes into sines. That's when we start thinking about identities not as statements of fact, but about as cool tools that we can use. If we find ourselves in a situation where we think to ourselves, I really wish that that sine was a cos, this might be an avenue to do that. Now, of course, we haven't seen any situations yet where we want to turn a sine into a cos, but if it does come up, we're going to remember this little fact here. Okay. So for the next section, let me just get rid of these angles that I don't need anymore and this point. For this next section, I'm going to start with 2 points on the unit circle, and I'm going to call them P and Q. And they can be anywhere I like around the unit circle. It can be here, it can be around over here. But I'm going to just start them both off in the first quadrant. Okay, let's connect these up and make a triangle. I go like this, 1, 2, and 3. So notice that I have 2 points moving independently around the unit circle. And I form a nice triangle. We know lots and lots of stuff about triangles. One of the things that we learnt when we were looking at trigonometry earlier was things like the area of a triangle, the sine rule, the cosine rule. Whenever we have a triangle, I said back in the earlier part that if you understand triangles, you can understand pretty much everything in geometry because you can break everything up into triangles. And we're going to do the same thing here today. So to start with, I'm going to introduce some angles. This one and this one. As I move the point around, I have this point Q and its angle around from the x-axis, I'm going to label capital A. So you can see that as I move Q, B doesn't change, but A does. While I'm moving this around, I want you to think about how A and B are related and how and whether A and B change at all. Okay, so as I move Q around, A changes, but not B. As I move P around, you'll see B changing, but not A. And once again, think about how lowercase a and lowercase b are related, and whether or not they change. Okay. So having played with these points a little bit, I'm now going to introduce an angle, this one here, the angle inside the triangle. This time, as I move point P around, B changes, so B minus A changes as well. And as I move Q around, A changes, so B minus A changes on top. I'm also going to introduce, I'm going to turn this one off for a second, and I'm going to turn this one off too. If this is angle B, what can I say about P in terms of its X and Y coordinates? Well, if I put the angle B into the cosine function, I'm going to find its horizontal distance. And if I put the angle B into the sine function, I'm going to find its vertical height. So the coordinates of point B are cos B and sine B. Similarly for Q, I'll turn this one off and then I'll turn this one on. This is A here. And so that means that Q is cos of A and sine of A. As I move Q around, wherever I end up, if I put this angle into the cosine function, I will find its horizontal distance. If I put this angle into the sine function, I'll find its height. So let's add in those angles once again. Okay. The first thing we're going to do to try and tackle what we know about this triangle is we're going to go back to something that I mentioned before about lowercase a and lowercase b. Now, you may have guessed that lowercase a and lowercase b are in fact the same. There they are, laid on top of each other. All the way back at the beginning, I mentioned that the unit circle is all the points that are exactly distance 1 away from the origin. So we already know what A and B are. They're both distance 1, and they always will be. C, of course, changes. Sometimes C is really, really small, and sometimes C is really, really big. So what determines how big or small it is? Well, one thing we can observe is that when B minus A is small, C is small as well. And then as B minus A gets larger, so does little c. That's the first observation. The other thing I wanted to mention is a trigonometric identity, which is so close to being universal that if you understand this from a geometrical point of view, when I put it up, you're not going to be surprised at all. Sine squared theta plus cos squared theta equals 1. If you're thinking about it in terms of the picture, it makes total sense. and I don't have to explain anything to you. But chances are I'm going to have to explain it. And one of the things is that it looks a bit confronting, doesn't it? All these squares and Greek letters. Maths was bad when they put letters in it, then they put Greek letters in it. Yeah, so sine squared theta plus cos squared theta, what's going on here? Well, this is just saying that the height squared plus the horizontal distance squared is equal to the hypotenuse squared, which is 1. That's all this is saying. So we thought about it in terms of the geometry first, but this is the algebraic identity, which is going to allow us to unlock a few more things going forward. Okay, now, this next proof shows you one of the most classic ways to prove things, and we've been doing it already this whole time. The principle is to calculate a particular value that you're interested in 2 different ways. The value that we happen to be interested in right now is the value of little c. The first way that I'm going to calculate the value of little c is by using the cosine rule. Let me just turn off little b, big B and big A. And you can see that this is a triangle where I know the 2 distances here and here, and I have an angle in between them, b minus a. And I should be able to calculate c, or at least express c in terms of this angle. So let's do it. And it looks like this. Well, let's start by writing out the cosine rule. Little c squared is equal to the square of the other 2 sides minus twice the product of those sides times cosine of the angle between them. If you cover up this part, it's just Pythagoras' theorem. But the way that you know that you're using the cosine rule correctly is that the c squared is opposite the angle you're referring to. So in this instance, capital C is actually this angle b minus a. So let's plug in what we know. We know that a is 1. It's a point on the unit circle. We can also think about applying this identity, but it's better to just think about it's a point on the unit circle. So this distance is 1. B is also 1. And we have to subtract 2 times a times b, well that's easy, it's just 2 times 1 times 1, times cos of this angle. Ah, I have just realized that this whole time I had this around the wrong way. How silly of me. Okay, I'm going to change this now and pretend that this never happened. I bet a bunch of people were confused when I was talking about how these are subtracted from one another. That makes a lot more sense though, doesn't it? This is A, this is B, and this is A minus B. Sorry about that, everyone. All right. So that should be A minus B. Fixed. We'll fix it in editing. Okay, and then we'll go to, there's a lot of arithmetic there that we can simplify. 1 squared plus 1 squared, well, that's just 2. And 2 times 1 times 1, we'll get rid of that. And we think to ourselves, okay, I don't know what to do with this thing. 2 minus 2 times cos of A minus B. Okay. But we've calculated C one way. We've used the cosine rule and the triangle that I have drawn up on the screen here. We're going to try a different triangle now. What triangle? We're going to use the triangle we get when we introduce these 2 lines. So we draw a horizontal line through P, and we draw a vertical line through Q. And they intersect at this point that I'm going to call U here. like so. And for the moment, I'm actually going to forget about some of these other segments. I'm going to get rid of this, I'm going to get rid of this, and I'm going to get rid of this. So those A and B and A minus B, they're all still there. But right now, what we care about is this triangle here. And we're going to be using, so once we've got this point, I'm going to get rid of the lines that I use to find the point U. GeoGebra is nice because the point still sticks around even when the lines are gone. And then I'm going to draw it up as segments instead. So what I have here is a right-angled triangle with C as its hypotenuse. And what is going to be the length of this side? And what's the length of this side? Think about the coordinates that I have provided here and here. How would you express this? How do you find the distance between 2 points anyway? Well, this time, what we can do is use the point distance formula. So this squared is equal to the x2 minus x1. So if I take cos A, which in this case is a negative value, and then subtract cos B, I get the entire length like this. It'd also work if I did cos B minus cos A, because I end up squaring it at the end. So this length here is from the x-axis to P is cos B, and from the x-axis to U is cos A minus cos A. Putting those distances together gives me the length of this side, and then I square it. What about this one? Well, this time I take the difference. Sine A is all of this from Q down to the x-axis, whereas sine B is from P down to the x-axis. And if I subtract sine B from sine A, I'll get this length here. Okay, so this is using Pythagoras' theorem rather than the cosine rule. Okay, so what happens next is we turn our algebra up and we expand it out. It's just 2 squares. But one thing you'll notice is cos squared A plus sine squared A. Cos squared A plus sine squared A, that's just like sine squared theta plus cos squared theta. That's going to give me a 1. It's always best using this rule in reverse. Find a bunch of really complicated stuff and you go, that's nice. Cos squared A plus sine squared A is 1. And then it simplifies down. And similarly, I've got a cos squared B and a sine squared B. Grab those together, turn it into a 1. And so I've got a 1 from sine squared A plus cos squared A. And I've got another 1 from sine squared B plus cos squared B. And I've also got minus 2 cos A cos B minus 2 sine A sine B. Let's gather all of that together. Where does the 2 come from? Cos squared A plus sine squared A gives me 1. Cos squared B plus sine squared B gives me the other 1. And then I've got minus 2 cos A cos B, and minus 2 sine A sine B, and I've just factorized it like that. Okay, I have now calculated C in 2 different ways, and I've gotten 2 different results. But they look pretty similar. This one says 2 minus 2 times something. This one says 2 minus 2 times some other thing. But they're both equal to C squared. 2 minus 2 times something, 2 minus 2 times another thing. If they're equal, then they're equal without the 2 minus 2 times as well. And so that's how we get our first double angle identity. Cos of A minus B is cos A cos B plus sine A sine B. This one is hard to remember, but thinking about this proof will go a long way. So I'm just going to put the other parts in so that we can remember how it was done. So I think to myself, I've got 2 points sitting on the unit circle. I've got one angle B, one angle A. Their difference is A minus B. And the triangle I get out of this, I'm going to do the cosine rule. That's one way. The other way is to take each of those angles and put them into sine and cos to find the coordinates, and then use Pythagoras' theorem to find the distance. And I've had it over there, but it still works when it's over like this. All of the same ideas still work. I'm still doing the same equations, no matter where they lie. Oh. And I get this result. Okay. So what I'm going to go through next is how to find the other double angle identities. And we're going to be using these to do it. So first of all, what happens if it's cos of A plus B? This is cos of A minus B. Well, we're going to do a little trick. Cos of A minus minus B. Why on earth would we do this? Well, we know that cos of A minus minus B, we know that minus minus turns into a plus. Why would you break a plus into two different minuses? But it's because we already know what to do with a single minus. So just applying this identity straight away says that cos of A minus minus B, well, that'd be just the same as up here, but I replaced the B with a minus B instead. And that's when we can start thinking about these identities up here at the top. Cos of minus B is cos B. Sine of minus B is minus sine B. I can get rid of this minus sign, and I can pull this minus out the front. And that gives us our next identity. Typically, it's written first because plus always comes first because it's like the first child and it always, gets everything. I'm not bitter. It's like the older sibling, I mean. The minus sign comes second, but the minus sign is actually the one we use to prove it. Okay, so we've proved this one, and that gives us this other one. So if we ever want to if we know the cos and sine of two different angles, we can find the cos of their sum and the cos of their difference just by taking appropriate products and sums or differences. What about sines? Well, you might remember I was talking before about how these identities let us turn sines into causes and causes into sines. And we're sitting here thinking to ourselves, I got these causes. I really wish they were sines. Well, have I got the trig identity for you? What we're going to do to find sine of A minus B is we're going to use this identity here, but we're going to do it in reverse. So I start with sine theta, and I turn it into cos of pi over 2 minus theta. Well, over here, I start with sine of A minus B, and I turn it into cos of pi over 2 minus A minus B. It's a little bit complicated to say out loud, but just think about how if A minus B is a single blob, then sine of blob is cos of pi over 2 minus blob. Okay. Now we're going to do a little bit of re-bracketing here. Notice that I'm subtracting something and I just expand the brackets. But what this gives me is cos of this thing, pi over 2 minus a, plus b. And we're going to be able to use this identity, except instead of capital A, it's pi over 2 minus a. This says cos of blob 1 plus blob 2 is this thing. Well, now blob 1 is a little bit more complicated, but the structure is going to be the same. So cos of something plus some other thing, we just run it through the algebra machine, and it says it's cos of the first thing times cos of the second thing minus sine of the first thing times sine of the second thing. Now this, cos of pi over 2 minus a, where have I seen that before? Ah, maybe I can go backwards again. So cos of pi over 2 minus a, well, by using this identity in reverse, I can turn this into sine. Similarly here, minus sine of this thing, well, sine of this whole business is going to give me cos. And that's where we get our next identity. Sine of a minus b is sine a cos b minus cos a sine b. And we're going to use exactly the same trick that we did before for cos by turning sine a minus a plus b into sine of a minus minus b and using some of these identities above. And we get this final identity here. And once again, they're almost always presented like this. When you see it, you'll see sine of a plus b, cos of a plus b, and then you'll see sine of a minus b after that, and cos of a minus b after that. This will be in your little table, and they'll say, go and memorize this table. But the order in which we found these identities was actually starting with the last one. Then we found the second one. Then we found the third one, and it was only right at the very end that we found that first one. So what we see up on the screen here is a whole bunch of algebra. I'm just going to get rid of some of these working ones because I don't think we need those anymore. This one. And we can get rid of these ones as well. This one, and 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 this one. So all the way around here, you can see all the different identities that we've found and explored today. Actually putting these to use is another thing entirely. But what we've done is we have learnt a lot about the symmetries inherent in the unit circle and in trigonometry. We've built ourselves an enormous toolkit, and we've already started to learn about how we can take the tools that we build and bring them together to build more tools to discover even more things. And also, time and time again, we've practiced the fundamental principle of geometry, algebra, and a lot of mathematics. If you want to know more about something, try and express it in two different ways and see if you can find an equality to understand what's going on. So, in lieu of suggestions for next week, I'm just going to pick something that I think is awesome and show you guys around. But it's been a pleasure introducing you to trig identities. There's way more trig identities. But if you follow through this and keep that mindset of making sure you understand the picture before you jump into the algebra, you'll end up in a much better position going forward. It's been a pleasure. Thank you all, and I'll see you next week.